Good evening, all. This particular module is to talk about a simulation that we're going to be running this week, or actually you're going to be running this week. You're looking at Scholar, and I'm going to this week's assignments. So we're coming up on October 3rd through the 9th. And this week we'll be talking about air temperatures. And so you see that you have an air temperature, a YouTube video, a PowerPoint, and then I give you two small YouTube videos on weather balloons and the role that they play in meteorology. So note, before you attempt lab number 4 this week, make sure that you first view Launching a Weather Balloon Part 1 and also Part 2. You click on this and it'll pull up a YouTube video. As you see, it's a 4-minute video with some crazy music. This particular one is only 2 minutes 37 seconds. So again, be sure to view these. Now for lab number 4, if I go ahead and click on lab number 4 here, you see it is a Word file that you'll download and bring up on your computer screen. And it is on radiation simulation. So notice the term radiation. Obviously that has something to do with Chapter 2, because Chapter 2 is about radiation. And now we're going to find out, or I'm going to find out, how well your knowledge base is and if you can successfully apply the principles learned in Chapter 2 on radiation to real world situations. So this particular lab has 2 parts. Part 1 is to draw the temperature curves from the data that you'll plot when you run the radiation simulation, and I'll show you how to run that in just a moment. So you go to the next page, which is this page over here, and notice I've got surface, day, and night, along with the different surfaces. You'll have a sand surface in the simulation, plowed field, grass, and snow. Now I've actually put a graphic in here which is temperature versus height, and that'll make more sense here in just a moment when I show you the simulation. And on this particular part, you're going to sketch what you see when you run the simulation. So you'll sketch here in part 1 the temperature, how temperature changes with height over sand during the day and at night. So you'll just sketch these in. You get to part 2, and I have 5 questions for you that you will refer to from your part 1 here. So from the sketches that you make in part 1, you will address 5 questions that I've placed here. So relatively short lab in terms of pages. You've only got a few pages here, but it will take you a while to complete, so you want to make sure that you start this as soon as possible. Okay, so to be able to run the simulation, also you have an exam this week as well. Exam number 1 on chapters 1 and 2. You see it's due here. Note that I'll give you 2 attempts at this. So you'll have 2 attempts to take the exam. It's multiple choice. I believe there are 50 questions. Like I said, multiple choice, and I'll take the higher of the 2 scores for that particular one for your grade. So let's talk about how to access the simulation. To do that, you're going to go here and click here to log into ThinkSpace. Again, that's where all the simulations for this semester are housed, or in this portal called ThinkSpace. So click here, and then from there, like I said, I invited you this past week to join ThinkSpace, and I asked you to join ThinkSpace by no later than Friday, October 2nd. So once you've joined it, you'll go ahead and enter your email address that you joined with. Actually, I'm going to use my wife's student account here so you can see what you would see as a student. So I'm going to log into ThinkSpace. It'll take a moment. Now let's just go ahead and make this a little bit larger here. You will now, from here, go into Simulation Sandbox. Click here. Note that I have the due date October 10th at midnight. So really it's Friday night. But as we go from Friday night into Saturday morning, so you actually have an extra 5 minutes from normal assignments to get this submitted. So click on Simulation Sandbox and then click on Radiation Simulation. Now, before you start working on RadSim, you will need to view the following YouTube video. This is the one that I'm recording right now. So you'll come in here, click on Directions for RadSim, and I'll show you that. Actually, as I'm thinking about this, this seems redundant because you need to view the video first. So just ignore this part right here. So ignore this part. I'm going to put the link up onto Scholar and have you do that first. Okay, so what you'll need to do, ignore this part and go in here and click on Start Case. Now you will notice here is a picture of a desert, and this is a weather balloon. Notice I can move the weather balloon up and down. I take the mouse and notice the heights here. Let me see if I can get in here a little bit closer to make this so you can actually see the different heights. So notice we take the balloon, which has a thermometer on it, and it's measuring the temperature at different levels throughout the atmosphere. So 0 meters is ground, and I can take this all the way up to 1,406 meters, which is 1.4 kilometers, which is basically 0.8 of a mile up. So with this weather balloon, we are taking temperatures at different levels from the ground up, all the way up to 0.8 of a mile. Recall that the 850 millibar surface, one of the maps that we look at, the map we look at for moisture, is roughly at about 0.9 of a mile. So we're not going very high in the atmosphere. We're going from the surface up to about the 850 millibar level. Okay. Now the key to this simulation, and I really want to emphasize this for you, is that you want to take temperatures at different levels of the atmosphere for all of these different surfaces. You see sand and sand during the day, sand and sand at night. And then you'll go over here and then go to snow, and you'll notice that you have a nice snowy surface during the day. If I click on night, you see the moon there. And this is real data. As you'll read in your lab, this was actually taken back in 1997. There was a weather balloon launched in Iowa that took the temperature from the surface on up to about 0.8 of a mile up in the atmosphere. So you're actually using real data for all of these. And then you've got plowed field for night and day, and the same thing for grass, day and night. So I'm going to run the first one for you. But before I do that, notice we have a graph over here on the right, and the graph is the altitude, so distance 0 meters is the ground level, all the way up to 1,500 meters, which is about 0.9 of a mile. Our balloon will only take data up to about 1,400 meters. Notice temperature is on the x-axis, and then you have your legend over here of the different profiles. So let me just let me show you. So for the first one, let's go to sand during the day, and our balloon, make sure it's on the ground and plot the point. Now you'll notice over here on the graph we see the temperature of 53 degrees at 0 meters. So for this particular day, for sand, it was 53 degrees on the ground. Now this is the key point here I want to make. When you move your weather balloon, make sure you only move it as high as the next level. So you have to move this balloon slowly. So it went from 0 up to 81 meters. Come down here, click on plot. Now, you notice that at 81 meters, the temperature has decreased by roughly a degree. It's now at 52 degrees. Okay, so grab your balloon. Oh, now notice how that jumped. So I'm going to bring it back down to 81 and slowly lift it until the very next data point, which is 163 meters. So plot that. Now as you look at this, what do you notice about temperature? How does the temperature change? You see it on the x-axis here as you go up into the atmosphere, as you go up in height. Well, you should notice that temperature is actually decreasing. You can see it from the graph. So let's grab this weather balloon again, and it's at 163 meters, and carefully move it up to the next plot point, 246 meters. Click on plot point, and I'll grab it again. So it's 246, move it up slowly to 329, and plot that. You don't want to skip, okay? You notice you can easily skip quickly. Okay, so we're going back down to 329, which was our last measurement. Move it up slowly to 414, plot the point. So again, you notice temperature is decreasing with height at a rather fairly linear rate. Go up to 500, which is the next one. We'll go ahead and plot. So you're getting the idea now. Again, carefully move the weather balloon until it changes the height. Okay, 587 to 674. 674 on up to the next one, 763, and again temperature's decreasing with height. Okay, we'll go up to 853, plot that point. Now we're up to 1034, which is basically 1 kilometer or about 6/10 of a mile up. 1034, moving it very slowly to 1126. Okay, that's as high as I can go, 1406. So notice a rather linear decrease with temperature with height. So now what you're going to do at this point, take your balloon back down to the bottom. We're now going to plot for sand at night. Okay, so you see it's changed. Our balloon's at the ground. We'll click plot point. Now notice sand at night. At the surface, the temperature was quite cool. Here during the day at the surface it was 53 degrees, but at night 41. That should make sense, you know. Typically it's cooler at night compared to the day. Typically, not always. Okay, so we're going to take this weather balloon and carefully move it up until the height changes. Okay, come on height, you need to change. Oh, there we go. So it went from 0 to 81 meters. Plot that. Now, something kind of odd should be appearing to you at this point. What do you notice about temperature as the weather balloon goes up in height? Temperature is actually increasing with height. That seems a bit odd, right? So we'll move this weather balloon up. Oh, that jumped. So 329 to 414. Okay. Oh, check this out. At 500 meters, half a kilometer, about 1/3 of a mile up, the temperature at night is the same as the temperature during the day. Okay, I'll continue to plot. In fact, this looks really odd. The temperature at night is the same as the temperature during the day at this point. Not exactly what you might have expected. But again, this is real data taken with a real weather balloon. Make sure I get all the points, not missing any of them. Okay, so what you'll do now is you'll take your picture here. Let's bring up here. And you'll go ahead and see if I can put this on at the same. So for sand, during the day, you'll sketch this part on here. Just give me a rough sketch. And then you'll take the nighttime temperature profile of sand and sketch that on here. And the reason you're sketching these, because like I said, you're going to be answering questions back here later on. Okay. So once you've done day and night, then go ahead and clear the graph. Let's switch to snow, and then you'll do the same thing. Bring the balloon down to the surface. Plot the temperature. So here it's about 32 degrees. Bring it up slightly to 81 meters. Plot that. So you get the idea. So this should be pretty clear to you at this point what you're doing. And if not, you can certainly let me know. But, so, plot your points, clear your graphs out. We've got a submit button here, but what I'm having you do is take your data here and putting it on your lab number 4 here. So I don't think it really matters whether you submit it or not. Okay, well, good luck with that. Actually, let me go ahead. Well, it has nothing to do with luck. You've got videos, you got PowerPoints. So I'm going to find out really how well you understand radiation. And here's a hint. You've got 3 energy sources that you're dealing with. That's right, 3 sources of energy. Keep that in the back of your mind. So the first question you'll see here, what did you notice about ground temperatures of each of the different surfaces? Looking at ground temperature of sand versus snow, or plowed field versus grass, those types of things. Tell me what you noticed in terms of differences. And then not only tell me the differences, but why you think these differences occurred. Because I talk about, be sure to use the concepts presented via the video and textbook in Chapter 2 in your response, specifically the energy sources that are present. And then you've got question 2, 3, 4, and 5. So question 2. What factors contributed to the vertical temperature profile? In other words, an increase in temperature with height up to 600 meters over snow at night. Now that's interesting. When you run the simulation, you'll see that. Again, be sure to use the concepts presented via the video and textbook, and specifically the energy sources that are present. That's going to be the key component there. Okay. Well, let me know if you run into any questions. Have a good evening.